Liquids and solids. So as a review, gases have low densities in comparison to liquids and solids. Gases have indefinite shape, they assume the shape of their container, and gases have an indefinite volume, they're easily compressed. Gases have weak intermolecular forces relative to thermal energy. An example of a gas is carbon dioxide, CO2. Liquids have high densities in comparison to gases. They have an indefinite shape because they assume the shape of their container, but they have a definite volume. They're not easily compressed. Liquids have moderate intermolecular forces relative to thermal energy. An example would be liquid water. Solids have high densities in comparison to gases. Solids have a definite shape. They do not assume the shape of their container. And solids have a definite volume. They are not easily compressed. Solids have strong intermolecular forces relative to thermal energy. An example of a solid would be sugar. Solids may be crystalline, ordered, or amorphous, disordered. And we'll get into solids and what crystalline and amorphous means a little bit later in this lecture. So this is a diagram showing gases, liquids, and solids. So gases, indefinite shape, indefinite volume. So they're going to expand to fill the volume of the container. Liquids have a definite shape, indefinite shape. They're going to take the shape of their container, but a definite volume. Solids have a definite shape and a definite volume. Intermolecular forces. The specific interaction between the molecules in coffee that taste bitter and the taste receptors on the tongue that is caused by intermolecular forces. Inter means between. Molecular is talking about molecules. So it's attractive forces that exist between molecules. Living organisms depend on intermolecular forces for many physiological processes. If, for example, let's say you want to eat a hamburger and your digestive enzymes are going to break down the protein, carbohydrates, and lipids within that hamburger. You can't do that unless the enzyme is actually attracted to the molecule that it needs to break apart. That's intermolecular forces. Every process that happens inside the body is dependent on that. Imagine breathing in oxygen. In order to breathe in oxygen, it has to be accepted by an oxygen carrier transporter in the blood. That's hemoglobin. And there's an iron group in hemoglobin that is attracted to that oxygen. So when oxygen gets breathed in, it goes all the way down to the extensions of the lung called alveoli. And at the point of the alveoli, on the other side, on the outside of the alveoli, the inside of your body, it's a blood vessel that contains red blood cells. And those red blood cells contain hemoglobin. The oxygen is going to diffuse through and it's going to bond to that or interact with that iron in the center of the heme group in hemoglobin. Intermolecular forces allows for the transport of oxygen through the body. And those are just a couple examples of how important intermolecular forces are. Less specific intermolecular forces exist between all molecules and atoms. These intermolecular forces are responsible for the very existence of solids and liquids. So, again, the various forces of attraction that may exist between the atoms and molecules of a substance, that's what intermolecular forces are. And intermolecular forces can be abbreviated IMFs. IMFs are a result of electrostatic phenomena. IMFs are non-covalent forces. So we learned about what a covalent bond is. A covalent bond is when it's a very strong bond where you have an equal sharing of electrons, and those bonds are really tough to break. Intermolecular forces are not going to be that strong. A lot of times they're just hydrogen bonds or weaker forces that are going to hold them next to each other. Kinetic energy provides the energy required to overcome the IMFs. Intramolecular forces are the forces that hold atoms together in a molecule. Intra is different from inter, so it's important to make a note of the difference there. The differences in the properties of solid, liquid, or gas are a result of the differences in strengths of the IMFs that make up each substance. So you can see a crystalline solid has a very high IMF. Intermolecular forces are strong. Those molecules are going to stay close together. As you increase the kinetic energy, in other words, you increase temperature, which is going to increase the energy applied to the system, that solid that has that strong intermolecular force is going to start to melt to a liquid. And when it melts to a liquid, the intermolecular forces decreases. So with increasing temperature, we have decreasing intermolecular forces. Eventually, that liquid is going to evaporate to a gas. And when it turns into a gas, we don't have very strong intermolecular forces. Those gas particles are going to be independent of each other. And that's, again, when we increase temperature even further, we're going to decrease the intermolecular forces. Intermolecular forces can be seen in everyday liquids. We're going to talk about surface tension and viscosity. So a paperclip will float on water if it's carefully placed on the surface of the water. It is held up by surface tension. You can't float a paperclip on gasoline because the intermolecular forces among the molecules composing gasoline are weaker than the intermolecular forces among water molecules. So surface tension has to do with the intermolecular forces that exist between water molecules. Those intermolecular forces allow for light substances to float on top of the water. Viscosity is the resistance of a liquid to flow. Viscosity is important when we talk about blood pressure in the body. So if you have, if you don't have enough hydration, that's going to cause your blood to not flow properly. So you're going to see a decrease in blood pressure when you have higher viscosity blood. It resists the flow of blood through your blood vessels. So viscosity, again, is the resistance of a liquid to flow. Liquids that are viscous flow more slowly than liquids that are not viscous. Motor oil is more viscous than gasoline. Maple syrup is more viscous than water. Viscosity is greater in substances with stronger intermolecular forces because molecules cannot move around each other as freely, which hinders the flow. So if we have a very viscous substance, it has higher intermolecular forces. Long molecules, such as the hydrocarbons in motor oil, tend to form viscous liquids because of the molecular entanglement. And this just shows maple syrup, how those molecules interact strongly. They have high intermolecular forces, so it flows a lot slower. So related to the topic of liquids, liquids can evaporate and they can condense. Vaporization is when a liquid is converted to a gas or vapor. In an open container, vaporization continues until all the liquid is converted into vapor. So again, liquid to vapor. In a closed container, the process of vaporization is countered by the process of condensation. So the liquid is going to go to vapor, but then vapor gets turned back into liquid. And that will eventually go back and forth until a dynamic equilibrium is met. Once its equilibrium has been met, the process of going from a liquid to a vapor, so vaporization, and the process of going from a vapor to a liquid, or condensation, is going to happen at equal rates. Another word for vaporization is evaporation. Because molecules on the surface of a liquid are held less tightly than those in the interior, the most energetic among them can break away into the gaseous state, and that's called evaporation or vaporization. In evaporation or vaporization, a substance is converted from its liquid state into its gaseous state. Now, condensation is the opposite. It's a physical change in which a substance is converted from gas to its liquid state. Again, evaporation and condensation, or vaporization and condensation, are opposites. Evaporation is liquid to gas, and condensation is gas to liquid. At the point where the rates of condensation and evaporation become equal, dynamic equilibrium is reached, and the number of gaseous water molecules above the liquid remains constant. The vapor pressure of a liquid is the partial pressure of its vapor in dynamic equilibrium with its liquid. So these are two examples of condensation. So we see condensation on this glass here. So there's moisture in the air. At any given time, there's water that's been evaporated in the air. Now when the water hits the glass, and the liquid inside the glass has a colder temperature, what's going to happen is cold causes things to condense. So the water vapor is going to hit the cold glass, and it's going to condense down into a liquid. So from its gaseous state floating around in the air, it's then going to condense down into a liquid. My kid saw this, thought that water was actually leaking through the glass. Sure, some of you may have thought that as a kid. Water doesn't go through the glass. Water exists in the air, and it's condensing on the glass. And the reason why it's condensing on the glass is because the inside has a cold liquid. If the inside had something like coffee, and it's very hot, you would not see condensation happening on the outside of that coffee cup. And that's because heat causes evaporation or vaporization. So if this was a hot liquid inside, you'd never see that condensation happening on the outside. Here is an example of condensation on a lake. So the temperature of the lake is colder than the temperature of the air. So all the water vapor in the air is going to condense onto the lake. The rate of vaporization increases with increasing surface area. So if you have a larger surface, you're going to have a lot more evaporation happening. Increasing temperature. So the hotter it gets, the more evaporation is going to happen. Decreasing the strength of intermolecular forces. That's going to depend on adding substances to a system. So if you add substances that can interrupt those intermolecular forces, then you're going to see more vaporization. Liquids that evaporate easily are termed volatile, while those that do not vaporize easily are termed non-volatile. So those are two definitions that you should make a note of: volatile versus non-volatile. After equilibrium has been reached, the number of molecules in the gas phase does not change with time. Therefore, the pressure exerted by the vapor over the liquid remains constant. The pressure of a vapor in equilibrium with a liquid is called vapor pressure. Vapor pressure increases with increasing temperature and decreasing strength of intermolecular forces. Vapor pressure is independent of surface area, though, because an increase in surface area at equilibrium equally affects the rate of evaporation and the rate of condensation. So this is a phase diagram. And the phase diagram is something that you're going to have to be able to look at and identify different components of. So here you can see on this side, it's like a chart. So we have increasing pressure on this axis and increasing temperature on this axis. And then we have some points that happen in between here. When we see to the left of this line, the material is in its solid state. When we see to the right of this line, the material is in its gaseous state. And when we see in between these two, the material is in its liquid state. If a substance is held at a constant pressure and the temperature increases, we're eventually going to see melting. If a substance is held at a constant pressure and the temperature decreases, we're going to see freezing. Melting is taking a solid to a liquid, while freezing is taking a liquid to a solid. Again, if we go to a constant pressure, and we're over here now, if we keep it at a constant pressure, excuse me, and we're going to increase the temperature, we're going to have vaporization occur. Vaporization is going from a liquid to a gas. Sorry about that. If we hold a substance at a constant pressure and we go from a higher temperature to a lower temperature, you're going to see condensation happening. And we're holding that constant, and we increase the temperature, we can go from a solid directly to a gas through the process of sublimation. If we have a substance at a particular pressure and we decrease the temperature, we can go through the process of deposition, and that's where we go from gas directly to solid without meeting that liquid state. So, you should be able to read these and determine the answers based on what you're seeing in the diagram. So the material is at 6.7 atm and 305 K. What phase is the material in? So 6.7 is close to here. And if we go over to 305, we see that it's in a gas. The material is pressurized at 4.5 atm. What temperature would the material have to be in order for it to be a liquid? So at 4.5 atm, we're about here. Now what temperature would we need in order for it to be a liquid? Well, we would actually need it to be a higher pressure. So the answer to this one is it's not possible. Boiling points. When the vapor pressure of a liquid increases enough to equal the external atmospheric pressure, the liquid reaches its boiling point. The temperature at which a liquid boils depends on the pressure above it. The normal boiling point of a liquid is the temperature at which the liquid boils when the pressure above the liquid is 1 atm. During the boiling process, temperature remains constant. So if you put a thermometer in boiling water, throughout the whole time that water is boiling, it's going to stay at a constant temperature. So again, the boiling point of a liquid is the temperature at which the vapor pressure of a liquid is equal to the external pressure above the liquid. So where is the boiling point of a liquid higher, at sea level or in the mountains? At sea level, since the atmospheric pressure is higher. So up in the mountains, the pressure decreases. So a lot of people think that at high altitudes there's not as much oxygen up there, and that's not true. The atmosphere has the same concentration of gases no matter where you are. The problem is the pressure up there is a lot less. So when you travel into higher altitudes, you're getting a lot less pressure. And that decreased pressure is causing less oxygen to go into the lungs. And that's where you can have altitude sickness, dizziness, weakness, eventually pass out from lack of oxygen. And that's why they say slow incremental progressions to higher altitudes is recommended. But boiling points. So in order for a liquid to boil, the vapor pressure of the liquid has to be equal to the external pressure above the liquid. So if we start traveling into higher altitudes, we are going to start seeing lower boiling points because there's less pressure. It's going to be easier for a liquid to boil at higher altitudes because there's not as much pressure. So the normal boiling point is the temperature when the vapor pressure is 1 atm. So this just shows boiling points of ethyl ether, ethyl alcohol, and water. So you can see the temperatures at which these boil. Water is going to boil at 100 degrees Celsius. Ethyl alcohol is at about 78. And ethyl ether is at about 34. So the vapor pressure curve for water is given below. What is the boiling point of the water at 300 millimeters mercury? So in order to read this graph, you would have to go to the 300 level and then go over until you hit the curve. So right here is where it hits, and then you go down and you can get your answer there. So they're saying 76. I think it's closer to like 78 based on this, but that's the closest answer that they're providing. The freezing point or melting point is the temperature at which the solid phase of a substance is in equilibrium with its liquid phase. We add ice to keep our drinks cool. What is the temperature of iced water? Roughly 0 degrees Celsius as long as there is ice present in the glass. So if you still have ice cubes floating in the glass, it should stay at 0. As soon as all of the ice melts, that's when the temperature is going to start to increase. A solution with a lower freezing point will have a higher boiling point. It has to lose more heat to freeze and gain more heat to boil it. So this is a typical heating curve, and it shows when temperature is increased and the amount of heat added is increased. So we start out in the solid phase, and we're going to increase the amount of heat that we're adding. So as we add more and more heat, eventually it's going to get to the point where it melts. So melting, as it's melting, it's going to be at a constant temperature. Then we're going to keep adding heat. So here we're going to increase the temperature as we add more heat, and the liquid eventually is going to begin to boil. So now this is in its liquid state, and this is when boiling happens. As long as that liquid is boiling, it's going to have that constant temperature. Eventually, all the liquid is going to be boiled, and you're going to increase adding heat, and you're going to see that gas state. So here is when it's in its gaseous state. So here is another example of heating curve. So you have solid down here. This solid is going to melt. Then you have liquid. The liquid is going to evaporate. And then you have the gas or the steam. The heat of vaporization is when it's going to evaporate, and the heat of fusion is when it goes from liquid back to solid. So the heat of fusion is required, or the energy required to change 1 gram of solid at its melting point to liquid. The heat of fusion for water is 335 joules per gram. Calculate the amount of heat needed to melt 25 grams of ice. Well, you would take 25 grams times the 335 joules over 1 gram, and that gives us 8,380 joules. Heat of vaporization is the energy required to change 1 gram of liquid to a vapor at its normal boiling point. So the heat of vaporization for water is 2,259 joules per gram. Calculate the amount of heat needed to vaporize 25 grams of water at 100 degrees Celsius. So 25 grams, we would multiply that by the conversion factor of 2259 per 1 gram, and that gives us 56,500 joules. So these are simple one-step unit conversion problems. You can expect to see these types of conversions on the exam. So heat of fusion, again, this is a simple example. Typically, when I do unit conversions, I would do the 25 grams, and I put grams on the bottom and joules on the top, because joule is the unit for heat. And this is our conversion factor. It's 335 joules per 1 gram. And then I would set that equal to, and then we would calculate the answer. So we still get the same answer, it's just I use the parentheses and the conversion factor, so it's a little bit more obvious. Same thing with this one. If I have 25 grams, I would put grams on the bottom and joules on the top. And now this is our conversion factor that says 2259 joules in 1 gram. And I set that equal to, and calculate the answer. Boiling. During boiling, thermal energy is not enough to cause water molecules in the interior of the liquid to become gaseous, forming bubbles containing gaseous water molecules. Once the boiling of a liquid is reached, additional heating only causes more rapid boiling. It does not raise the temperature of the liquid beyond its boiling point. A mixture of boiling water and steam will always have a temperature of 100 degrees Celsius. Only after all the water has been converted to steam can the temperature of the steam rise beyond 100 degrees Celsius. So the temperature of water as it's heated from room temperature through boiling, you can see here. So this is liquid water, it goes up to boiling. Once it starts boiling, it will remain at a constant temperature. And then as you continue to add heat, you'll see that gaseous stage, and when it's in the gas and all of the liquid has evaporated and all the liquid is done boiling, then you can start increasing the temperature of that gas. Evaporation is endothermic. Endo means inside of. Thermic is talking about heat or temperature. So when a liquid is converted into a gas, it absorbs heat because energy is required to break molecules away from the rest of the liquid. Our bodies use the endothermic nature of evaporation for cooling. When we overheat, we sweat, which causes our skin to be covered with liquid water. As this water evaporates, it absorbs heat from our bodies, cooling us down. High humidity slows down evaporation, preventing cooling. When the air already contains a lot of water, sweat doesn't evaporate as easily, and that makes our cooling system less efficient. This is why when some people start talking about dry heat or humidity, dry heat can be tolerated at much higher temperatures. Like in Arizona, you can tolerate much higher temperatures when there's dry heat because your sweat will evaporate more efficiently and take that heat away from the body. If you're at that same temperature and it's really humid, the sweating doesn't work as well, so it's more difficult to control our body temperature. Condensation is the opposite of evaporation, like we learned. It's exothermic. Exo means outside. So heat is released when a gas condenses to a liquid. As steam condenses to a liquid on your skin, it releases heat, causing a severe burn. The exothermic nature of condensation is also the reason that winter overnight temperatures in coastal cities, which tend to have water vapor in the air, do not get as low as those in deserts, which tend to have dry air. As the air temperature in a coastal city drops, water condenses out of the air, releasing heat and preventing the temperature from dropping further. In deserts, there's little moisture in the air to condense, so the temperature drop is greater. As the temperature of a solid increases, thermal energy causes the molecules and atoms composing the solid to vibrate faster. At the melting point, atoms and molecules have enough thermal energy to overcome intermolecular forces that hold them at their stationary points, and the solid turns into a liquid. When ice melts, water molecules break free from the solid structure and become a liquid. As long as ice and water are both present, the temperature will be 0. A mixture of water and ice will always have a temperature of 0. Only after all the ice is melted, as we discussed previously, will the temperature rise above 0. So a way to cool down a drink is to drop several ice cubes into it. As the ice melts, the drink cools because melting is endothermic. Heat is absorbed when a solid is converted into a liquid. The melting ice absorbs the heat from the liquid in the drink and cools that liquid. Melting is endothermic because energy is required to partially overcome the attractions between the molecules in the solid and free them into the liquid state. Freezing is exothermic. So heat is released when liquid freezes into a solid. As water in your freezer turns to ice, it releases heat, which must be removed by the refrigeration system of the freezer. If the refrigeration system did not remove the heat released would warm the freezer, preventing further freezing. Sublimation is a physical change in which a substance changes from its solid state directly to its gaseous state. When a substance sublimes, molecules leave the surface of the solid, where they are held less tightly than the interior, and become gaseous. Dry ice, which is a solid carbon dioxide, does not melt under atmospheric pressure at any temperature. And that's because of that phase diagram that you saw earlier. At minus 78 degrees Celsius, the CO2 molecules have enough energy to leave the surface of the dry ice and become a gas. So this is showing an example of sublimation. Dry ice is solid, carbon dioxide. The solid does not melt, rather it sublimes. It transforms directly from solid to gas. Regular ice will slowly sublime at temperatures below 0 degrees Celsius. In cold climates, ice or snow lying on the ground gradually disappears, even if the temperature remains below 0. Similarly, ice cubes left in the freezer for a long time slowly become smaller, even though the freezer is always below 0. Ice sublimes out of frozen foods. You can see this in food that has been frozen in an airtight plastic bag for a long time. The ice crystals that form in the bag are water that was sublimed out of the food and redeposited on the surface of the bag. Food that remains frozen for too long becomes dried out. This can be avoided by freezing foods to colder temperatures, a process called deep freezing. The colder temperatures lowers the rate of sublimation and preserves the food longer. So now we're going to transition to the last few slides talking about solids. So solids can be crystalline. Crystalline is a well-ordered array of atoms or molecules, or amorphous, where they have no long-range order. Crystalline solids can be divided into 3 categories: molecular, ionic, and atomic, based on the individual units that compose the solid. So this is the difference between a crystalline and amorphous solid. So crystalline has a particular structure to it. Amorphous does not. Crystalline solids can be molecular, where the composite units are molecules, and they have low melting points. Ionic, where the composite units are formula units, cations and anions, and they have high melting points. Or atomic solids. Composite units are atoms, variable melting points. So molecular solids whose composite units are molecules, ice and dry ice, are examples of molecular solids. They're held together by intermolecular forces, dispersion forces, dipole-dipole forces, and hydrogen bonding. Ice is held together by hydrogen bonds, and dry ice is held together by dispersion forces. Molecular solids as a whole tend to have low, moderate to moderately low melting points. Ice melts at 0 degrees Celsius, and dry ice sublimes at -78. Ionic solids are composed of formula units, the smallest electrically neutral collection of cations and anions that compose the compound. Table salt and calcium fluoride are good examples of ionic solids. Ionic solids are held together by electrostatic attractions between the negatively charged particles and the positively charged particles. So positively charged cations, negatively charged anions. In an NaCl, sodium chloride, the attraction between the sodium cation and chloride anion holds the solid lattice together because the lattice is composed of alternating cations and anions in a three-dimensional array. The forces that hold ionic solids together are actual ionic bonds. Since ionic bonds are much stronger than any of the intermolecular forces discussed previously, ionic solids tend to have much higher melting points than molecular solids. Sodium chloride melts at 801 degrees Celsius, while carbon disulfide, a molecular solid with a higher molar mass, melts at -110 degrees Celsius. And this is an example of that repeated structure of cations and anions. So when we go back and talk about the melting points of the ionic solids, this is why we put salt on our sidewalks to help melt ice. The salt will interact with the water, disrupting the bonds in the water. So that disrupts the intermolecular forces of the water. It also has a higher melting point. So it will cause the ice to melt at lower temperatures because it interrupts those molecular bonds there, or ionic bonds. Atomic solids are solids whose composite units are individual atoms. Diamond carbon, iron, which is Fe, and solid xenon are good examples of atomic solids. Atomic solids can be divided into three categories: covalent, non-bonding, and metallic. Copper is a metallic solid, and this is just a picture of that. So covalent atomic solids are held together by covalent bonds, and they have high melting points because covalent bonds are really strong. Non-bonding are held together by dispersion forces, and those have low melting points. And metallic are held together by metallic bonds and have variable melting points. So carbon dioxide and iodine are examples of molecular solids. Or carbon dioxide is a molecular solid, and iodine is an atomic solid.